What
The
happened?
trees on that campus.
The scenery during the summer is
Yep.
quite impressive.
Yeah, yeah. Okay, this is your half-life equation. And one of the exam problems asks to give a half-life example. And there's different ways to do it. And I'm just going to go, there's really nothing wrong with the Wikipedia page.
Just accurate enough for what we need for.
Yeah, and we're not going to argue over which is correct. There's sort of three different ways to describe what the half-life is. This is kind of the easiest one. This is the exponential, and this is the time constant. But the point is, if we come back to this this figure, we can see that we start with 10,000 particles now. In 8 days, we're at 5,000.
Already half.
Half, exactly. In 16 days, we're at 2,500, 1/4.
Yeah, excuse me.
So the math goes like this, this particular example. 0, 8, 16, 24, 32. It doesn't really look like 32, but it is. Okay, so time goes 0, 8, 16, 24, 32, and n, the number of particles, just goes by starts at 10,000. 10,000, 5,000, 2,500, 12, 1,250, and then 675. And what this is referring to is just the number of a certain type of isotope. So if we go back to, let's just look at one of these reactions. If we look at one of these reactions, if we started out with 10,000 of these particles, and every single radioactive element has its own half-life. Some are longer, some are shorter, and they're all across the map. But every one of them does something like this. So really what I'd ask you to do, I'm not going to do it now because of time constraints, go in here, type the equation, pop it into Microsoft Excel, and just do a plot. Just do a couple of plots so you're comfortable with it. And again, I've shown you the raw data here. This is your x-axis. This is your y-axis. Plot it, and you now know how to do extrapolation. So there you go. All right. So these are some of the early physicists kind of looking into, and these are scientists. This is before we really get to the engineering phase of nuclear energy. Enrico Fermi, so all these people, lived and died 150 years ago, 120 years ago. Not going to go into all their biographies. Here's something we briefly discussed last time. So if I shoot a neutron at uranium-235, remember uranium-235 is unstable because of the lack of neutrons. Uranium-238 is more stable because it has more. It becomes uranium-236, which itself is unstable. And I wish I had a good explanation for this, but the protons and neutrons are sitting there. Obviously, the protons are trying to force each other apart, and the neutrons are shields keeping that from happening. And they're moving, and it just so happens that uranium-236 is itself unstable. I don't know all the reasons behind that, but it's unstable enough that when it pops apart, you get these fission products. So we talked about the different products. We talked about the fact that gamma radiation is an electron, or sorry, is a photon. Beta particles are high-moving electrons, and then here are your neutrons. So the neutrons themselves become the bullets, if you will, to destabilize additional uranium nuclei, et cetera, et cetera. You get enough of them in one place, and you get a boomy. Okay. Here's Niels Bohr, and he, proposed one of the first models for what atoms actually look like. And if you go and look at the periodic table, let's look at the dynamic periodic table again. Take a look at the dynamic periodic table. It was really his idea to start setting up these orbitals in terms of, where are the electrons, why is there an up and a down? You can see right there, there's an up and a down electron right there. You get out into the larger.
But this means that it's full, though. That up and down, that means that
it means it's full, yeah.
And then if it's just an up, that means that there's a slot open.
Exactly,
Okay.
yeah. And that's why you see these lithium, sodium, potassium. These are the kind of the movers and shakers on the periodic table because they've got that one open S. These out here are full. They
Full,
just
yeah.
they're not reactive. So very reactive, not reactive. And it was the work of these folks. And at this point, Niels Bohr, 1885, and he was just born 20 years after the periodic table was assembled. And it was just kind of there ad hoc. He's like, well, why is it like that? And so he started, looking at this actual atomic structure
Wow.
before you could see it.
Wow.
And, can we see it now? Not really. I mean, there are atomic force microscopes where you can, see and touch individual atoms. But in terms of visualizing these things, I mean, remember they're 1,000 times smaller than light. A wavelength of light is 400 nanometers, and these things are picometers in diameter.
I'm thinking like here's a strand like it's so much smaller than a hair. Like the
Yeah.
thickness of a piece of a single hair.
Yeah, it's giant. Yeah.
Yeah, I think that's giant compared to.
Right, yeah. Okay, so there's Niels Bohr. And, as I mentioned, this is an example of what the small-scale nuclear reaction would look like. And, of course, we're talking about fission. We talked a little bit about last time the fact that iron occupies a special place on the periodic table where anything sort of below iron is undergoing fusion in a star, and then anything that we sort of do now with our fission is happening above iron. So the point
You're
is,
talking about like CERN?
well, no, I'm more or less talking about what happens inside a star, which is a nuclear reactor.
Yes.
And once you hit iron, you're sort of out of fuel.
Okay.
You're out of fusion fuel.
Got it.
On the other hand, if you're running a fission reactor, which is what we currently use on planet Earth, once you hit iron, you're out of fuel. So iron sort of
This
is.
is when they take the rods out and put like new rods in.
Yeah, and it's not, and I'm not saying that iron is a byproduct necessarily. There's all kinds of other byproducts.
Oh,
but,
yeah.
but it sort of sits at this special place on the periodic table between fission and fusion.
Okay.
So if you're like, well, what is that guy? Well, it's going to be, something.
So that's how it starts. It just starts with that one, photon?
Neutron.
Neutron.
Yeah.
It's the one that breaks it up, and then that's just a like.
Yeah, in the same way that you might start
Open the floodgates.
in the same way that you might start a fire. You light the match. I mean, there's oxygen all around. In this case, there's the only fuel is the instability in the nuclei. In the case of starting a fire, the instability is the fact that you have carbon and oxygen sitting right there ready to burn.
Okay.
And they're showing that, carbon itself could be a fission product, a light atom, and it's going to, sort of fly off somewhere. It may or may not be radioactive. If it is, it might have its own half-life. A neutron might fly out of it, so all kinds of fun stuff coming out of there. 94. So there's plutonium, which, can be made intentionally as a byproduct in a breeder reactor. But here is the nuclear reaction that leads to creating plutonium. So if a neutron comes in, collides with uranium-238, and then all of a sudden an electron or a beta particle comes off, you still have uranium, but that electron sort of left behind
Yeah, an open spot.
a neutron. Yep. So you've got this, the neutron, let's see here, came in, there's added the mass. Right, so when that electron comes off, you're left with NP, which is neptunium, which itself has a very short half-life, so it's just kind of hanging around very, very briefly. But that electron left behind a proton. If another electron leaves, now you've got plutonium.
Okay. So that's like a 3-step process to be able to get it to that.
Yeah, and it happens somewhat spontaneously due to the very short half-life of these two elements, of these two isotopes.
That's what I was going to ask.
Yep.
It's almost simultaneous.
Yep, yep. And it's statistical, it's not really predictable, it's just something that, happens to a large mass of these things. Okay, now this is one of my favorite figures in the whole book. As you can see, up here is our uranium mine. That's just what's sitting on Mother Earth. We send that off to the refinery, because we're going to take, just as you would do with iron, you're going to get rid of the stuff that's not iron, so you can make iron ores to make steel bridges, buildings, etc., etc. So you're going to refine the uranium off. That's mostly mechanical. Now you're going to go chemical, refine it even further in step C. Complex of uranium piles for preparation of plutonium.
That's just like staging area?
Well, there's a lot of processes going on, so you have to set up your reactors. So you could send some of your plutonium off to make power, because it itself is reactive. Here's F. I'm looking for the figure. And there are also a lot of other byproducts that come off. So if you say make radioactive carbon or radioactive iodine or radioactive bromine, it can then go off into for medical uses. It could also then be turned into bars, etc. But eventually, it all goes to this thing called N, possible subsidiary for making secret weapons. And I don't know. I don't know what the WikiLeaks.
Dry?
Well,
But the cool thing I heard is that you can test the metals and where in the world it came from because of the different chemical compositions. So
Yeah.
if it came from the Middle East versus North America.
yeah. And again, I'm not an expert on this. One of my colleagues there back at Drexel University was a nuclear physicist who was on the post-Chernobyl commission, and so we went in and said, hey, this is what we need to do to clean it up or, keep it from getting worse. And one thing he noted is that, and again, I'm just sort of parroting what he said. He said nuclear reactions are one example where more energy comes out than goes in. And obviously it's a violation of the first law, but this plutonium, there are plutonium reactors in some spacecraft, for example, and so it's still there as a potential fuel.
But
Anyway.
harnessing it?
Or, well, no, it's been engineered, but the other point is it's pretty nasty stuff, and it's kind of little too easy to make a bomb from.
So it's kind of like the moral versus the
Yeah, any technology can be used
whatever.
for good or evil, I guess is the point. So,
Yeah, I get it.
yeah, Yeah, and again, I don't know exactly where the plutonium is. I know there's a lot at the Savannah River site, but anyway, that's why you have to.
At where?
Savannah River site, in Georgia, there are a lot of breeder reactors there. And it's possible there's even a bunch sitting on these Minuteman missiles right up here in Montana. Okay, so here's some of the, this is actually what went wrong at Chernobyl. It was like the day after a big Russian holiday. Nobody really wanted to be working there. The core was going cold, and you don't want that to happen. So there were not enough fuel rods in there to run the reaction.
Keep it proper temperature.
To keep it running at the proper temperature, because really it's just a big boiler. You're
Okay.
just boiling steam in the same way you would in a coal-fired power plant, except you're using the heat from all these nuclei bouncing around. And the guy on duty panicked, stuck in more fuel rods, pulled out the control rods, and it went went nuclear. It exploded.
Vodka.
Too much vodka in the sauce. So, his fear of being the guy who let the reactor cool down ended up, he overreacted, like oversteering into the ditch, basically, and blew the place up.
You see that, there's a video of a guy that snuck into Chernobyl and was
Really?
camped out overnight, inside one of the buildings and stuff. And I'm just,
Apparently
With his
wildlife's
wetsuit.
thriving there.
yeah, and animals and everything, but you can't touch anything.
Well, right. I've heard similar things about these settling ponds over south of Butte. There's some big old fish in there because, well,
Well-
we haven't really been touching them that much. I don't know. I mean, what do you think?
I've actually fished over there.
Okay.
And there's not much in the way of fishing for the first two ponds.
Okay.
The third settling pond, there's
Yeah.
some fish in it. But what people are referring to when they talk about that is there's a hog hole over there.
Okay.
Off, outside, it's not connected
Oh, really?
to
Okay.
the actual settling
Okay,
pond.
okay.
But there's a hell of a lot of really big fish in
Yeah.
there. They stock it.
Yeah.
Where's this at?
It's like right off the highway as you're coming into Anaconda.
Got it, yeah.
Going towards Anaconda. But if you're coming into Anaconda and you look off to the left side of the road or the east side of the road, there's some huge settling ponds.
Yeah.
Silverboat Creek. And,
Okay.
So really, I look at this figure and it takes us all the way back to the Savory's coal miner's friend, right? It's kind of a nuclear version where you've got pressure vessels and water moving out. There's your pump, a little more sophisticated, but that's it. Concrete shield. This is what failed at Fukushima. They're still having trouble with over there.
I hear there's still just dumping a massive amount of contaminated water into the ocean.
I have heard that too. Yeah, and when we were in Japan in the spring, we didn't, we weren't allowed to go to Fukushima. We did go to Onagawa where they're rebuilding, based on their previous failures.
One of my layovers is in Tokyo
Oh yeah.
for the Vietnam trip.
Okay. Yeah, if you get a chance, check it out. It's a cool town. Lots going on. So this is gas cooled, and so you could think of the same way you think of a engine. And the reason for using CO2, it's not going to blow up. It's not combustible. It's inert gas. Graphite. There's your carbon as a absorber of neutrons. And then there's some other stuff in the book about the types of reactors, when they start up, when they shut down, a few other technologies, all kinds of ways to build them.
I heard that we're doing a lot of down phasing of the nuclear power plants and stuff. And,
We are.
We're just shutting them down just due to just being scared of it all, kind of.
Well,
The results of it. But if they're shutting all that down, then there's got to be an alternative.
Fukushima was really kind of the straw that broke the camel's back.